Okay. So good morning, and welcome to this memorial symposium for Sid Drell. Sid passed away in December of 2016, but to a great extent, he's still with us. He was a mentor to many people in this room, I think in general, a mentor to the entire laboratory. He set many of us on our scientific course in our careers. And so I'm really glad you folks are here for a symposium that will basically honor his memory. Sid was many things in the world. He was an expert on nuclear weapons and military policy, technology, an advisor to presidents, and of course an influence on many academic institutions. But I think it's appropriate here at SLAC to remember him in his principal role as a great scientist. With Panofsky, he was one of the creators of this laboratory. His scientific vision really set this laboratory on its course, and as an early creator of the laboratory, he also set the tone of the way research is done here. I must say, a breath of fresh air for those of us educated at these East Coast places like Harvard and Princeton. In 1958, he wrote 2 papers that expressed his vision that the fundamental interactions would be understood through electromagnetic probes. A paper with Charles Schwartz, which was the original paper on inelastic electron-proton scattering, and a paper, single-author paper, on the current status and future of quantum electrodynamics. In those papers, he set out a vision that this laboratory has pursued, and over the years, it's been extremely successful and led us to great understanding of physics. This memorial conference will be a little different, I think, from others that you've attended. There are no speakers from Sid's generation. I think rather it's a chance for those of us who are his intellectual children, grandchildren, and in some cases great-grandchildren to celebrate his legacy and to thank him for the progress that we've been able to make on the road that he set. So again, thank you very much for attending. The first session in this symposium will be about quantum electrodynamics, a field, again, that Sid recognized the importance of in the 1950s, claimed would be a road to understanding of physics beyond what was then known, and today we would say beyond the standard model, and a subject that was highly developed in the SLAC theory group, especially in the period around 1970, led by Tom Kinoshita and Stan Brodsky. So the first speaker is Jonathan Sapirstein. Jonathan was a student of Stan's in that era. He's gone on to become a professor at Notre Dame University. He's one of the experts in high precision calculation in quantum electrodynamics, and he'll talk about the current status of that subject. So thank you very much.
Well, thanks for the invitation to talk about quantum electrodynamics, which of course Sid played a very important role in a number of senses. And the context I'd like to put this talk in is a talk that Sid gave at the 60th birthday celebration for Julian Stringer down at UCLA. And I printed this old paper out. It's from 1978, and just found it to be a real gem, just his insights and approach to this field. There were just a number of things that I really found of great value, and I'm going to base a lot of my comments relative to that talk that he gave. But of course, a lot has happened in the interim. There was a conference in Warsaw last year that just where a great amount of progress was reported, and I'll report some of that. And one thing I'm going to do is, because Sid was quite interested in going beyond perturbation theory, I want to talk about a certain kind of effect in quantum electrodynamics that involves what are called binding corrections, which I'll explain presently, that can be treated in a non-perturbative way. That is something that I think he would have liked hearing about. Now, the title of my talk has to do with precision, and it's kind of, there are a number of points about going to many, many digits that were addressed in an old paper by a gentleman named Richtmeier back in 1932. It's called The Romance of the Next Decimal Place. I recommend it. It's a fun article that addresses this question. Why do we go past 1 or 2 digits? Well, the first thing he points out, of course, if you're going to talk about an exact science like physics or chemistry or what have you, you need something. You need a few digits at least. So certainly some degree of precision is necessary. But I think what's most important, and what I think Sid in particular would have found most important, is the idea that you can discover new physics in precision measurements and compared to precision theory. That's kind of the main point that I want to emphasize. So if you find a small deviation of a standard property, sometimes you'll discover new physics. Richtmeier talks about astronomical examples where small deviations led to new physics. But I'll be concentrating on the anomalous magnetic moment of the electron, and you'll hear about the muon presently. The reason I underlined standard is that there is a case where you can, for example, if the electron has a dipole moment, and all you have to do is see a non-zero dipole moment, you don't need precision to have made a discovery. But if you expect a certain property just from ordinary QED and are looking for extra physics, you need the tool of precision. One thing that I liked about Richtmeier's article is that he gave a quote from Michelson that we're going to add a bunch of digits just because it's fun. And I'm sure you all know examples of theorists who have the same problem of adding digits, even when you don't need them. It is fun, so there's a certain aspect of that, but I'll try to limit my comments to useful precision. Just one general note. I'm talking about very low energy systems. Atoms or an electron in a penning trap is a kind of bound state that has extremely low energy compared to high energy physics. The main thing that is happening is because QED is established, it's just a valid theory, we're beginning to use it as a tool to find out various properties of nuclei, because at some point the main source of error comes from the fact that there's some strong interaction present. And I will mention that currently the size of the proton is something that is controversial, and I will talk about that presently. Let me show you some of the precision experiments that I'll be talking about. I don't think I'm going to be able to get through all of them. But the first one, which Sid discussed in some detail in his talk because he really was interested in hydrogen hyperfine splitting, is very, very strongly contaminated by proton structure. And I put a little underline at the 7th digit there because that's where we start losing control of proton effects. So it's certainly possible to add those extra digits past the underline. They're not going to be something that they're not going to teach you anything on the theoretical side, but of course experimentalists are going to give the digits if they can. But that's an example of more precision on the experimental side than is necessary. One thing I'm going to be putting a big emphasis on is the splitting between the 1s and 2s states in hydrogen. This is something that there were significant improvements being made in 1978 when Sid gave his talk by Ted Hench down at Stanford. And that work has increased in precision over the years until it's just an astonishing 0.004 part per trillion measurement. Some of those digits are not necessary, but it's still a really marvelous benchmark. And it is used in conjunction with QED theory that I will be describing to you to get the most accurate value of the fine structure constant, which we need in order to compare the experimental electron G-2 measured by Gabrielsi to under a part per billion. In order to interpret that, we need the best possible value of alpha, and that comes from a combination of theory and this in a way that I'll be talking about. And if I have time, I will mention progress in fine structure of helium, another interest of Sid's. He spent some time talking about this, which can be used to get a value of the fine structure constant. And there's been recent progress that has gotten the experiments down to 4 parts per billion. It's not competitive with G-2, but it's still getting pretty good. And I'll tell you the status of that. And finally, if I have time, I want to tell you about a very accurate measurement of the mass of the electron that is done by measuring properties of hydrogen like carbon. In all cases, it's necessary to really understand QED and in the sense of the bound state problem, which is really quite a difficult problem, and people are working on it constantly to this day. Here's a picture of Schwinger holding a pen, which is all he needed to get that particular term, the alpha over 2 pi, and also actually the alpha over pi squared term his student evaluated. But beyond that, when Sid was talking, this number was only available numerically, but it's subsequently become available analytically, as has further terms. But let me just mention that you can get alpha basically from this term. This, by making this thing agree with the experiment, you can figure out what alpha is. There's a way of doing that. Okay, so now let me describe briefly what Drell talked about. And one unusual feature is, remember, this is Schwinger's 60th birthday, and Drell is congratulating him on his wonderful successes in particular the G-2. But he said, this is getting out of hand, and that's at a time when only 3 loops have been done. But let me show you this. There's Tom Kinoshita, who was just mentioned, and it's almost out of hand, but astonishingly, largely because of this man's efforts and advances in computers, we actually have been able to go to this level. Nevertheless, what Sid said is that this is getting really awkward. You just have to work harder and harder each order of alpha. Is there a way to do this thing non-perturbatively? And he asked Julian to directly do that, and in one of his tables, he has this imperious comment, which I'm sure Schwinger appreciated no end. So Sid actually worked on very fundamental aspects of the G-2, not the direct Feynman diagram calculations, but he had a very nice paper with Heinz Pagels, where he used dispersion relations to just get a kind of non-perturbative handle on the problem that made some progress, but the fact that the graphs can be done make it less germane. And a very nice paper, and I think we'll hear more about this later, about what if the electron has some substructure, what limits to G-2 agreement with theory, what limits come from that. Okay, now in 1978, he was using an alpha that came from solid state, and the experiments were only at 1 part per million. Let me tell you what you need to get to the present under 1 part per billion level. So the recoil value of alpha is an essential part of doing this comparison, and to get that, this started, a seminal contribution was made by Steve Chu, who realized that if you had cesium in an excited state and it decayed to the ground state with the emission of a photon, that if you could measure the momentum of the recoiling cesium atom, which is equivalent to, if you just applied Broglie, to measuring h bar over the mass of the cesium atom, if you can measure that, you can use the fact that the Rydberg, this R sub infinity, which is known to better than 9 digits, you can, and C is just defined. Mass ratios can be also evaluated with high accuracy. That this would be a good way to get a value of alpha that's good to the sub-part per billion level, which you need to compare with Gabriel's experiment. Now, there's no theory here, but outside of de Broglie, but to get the Rydberg is actually really, really hard. There's a lot of theory that I wanted to let you know about, and in particular, that theory involves doing stuff in a non-perturbative fashion. As an example, a very simple example, this is just the Dirac equation for the ground state of a hydrogenic ion with, if the nucleus is charged Z, this is just what you get from the Dirac equation. And this is an example of an exact function of Z alpha, this sort of thing that Drell was trying to get Stringer to provide him with. And in this case, you know what it is, just analytically, but you can also Taylor expand it. So there are two approaches to this problem of evaluating what are called binding corrections. A binding correction is something that depends on Z times alpha, even if Z is equal to 1. This is the convention used to indicate that this comes from something called the Dirac-Coulomb propagator. And there's a whole field of physics that I just want to allude to, which is studying QED in an extreme environment of, for example, uranium with just one electron. Hydrogenic uranium is a system that can be studied. Obviously, you want to work with this, but for the basic Dirac energy, but beyond that, what you need to do when you study radiative corrections, the Lamb shift, is you have to also work out radiative corrections in intense Coulomb fields. And this is something that's being studied intensively, and so far we're finding out that QED works in these intense Coulomb fields like in hydrogen, like uranium, quite well. And this actually, I wanted to note that Drell was very interested in testing the limits of QED in another direction, which is in high energy scattering tests. He played a big role in that. And again, QED has been tested to very high energies, but there you're working with free propagators. Okay, so there are in bound state QED a set of functions, a sort of function that in this case we actually can get. I'll show you how in a moment. That in this case, this is the one loop Lamb shift. And the one loop Lamb shift has a certain behavior that's understood, but that is pulled out of an unknown function, f of Z alpha. This originally was studied as an expansion in Z alpha because people were looking at hydrogen, and so you just work this term out. It's a little complicated because there's a logarithmic term. But the actual expression that you start with is, there's the Feynman diagram with the double line indicating this is not a free propagator. So it's a more complicated object called the Dirac-Coulomb propagator that is known best. It's easiest to work to represent in coordinate space instead of the momentum space we usually use. And it's been a problem for 70 years since people have started working with this, is that there's no known analytic expression for this object unless you do a partial wave expansion. And if you do that, and unfortunately a partial wave expansion involves an infinite number of terms, but if you do that, you can represent this thing, it's a bunch of Whittaker functions, and start doing calculations. And people have been doing this for a long, long time, but it's kind of remarkable that only in 1999 did a non-perturbative approach, where this is just directly evaluated, not Taylor expanded in Z alpha. It wasn't until 1999, Gensura, Moore, and Soff were able to really control this thing to the number of digits that you need. It's embarrassing to draw in this audience, for this audience to write down a one-loop diagram and say it's hard, but it's hard. So here's what you do in order to get this nice accurate value of alpha that comes from recoil. You need the Rydberg, but you don't have the Rydberg directly. You have the 1s2s splitting. Now, there's a somewhat complicated procedure that goes on because you don't know the Rydberg at first, and you don't know the proton size, which affects it. But so there's a certain fitting procedure that goes on. I'm just going to nail down a Rydberg and just show you what happens to this number. So first what you want to do is get rid of the Dirac energy. And by finite proton mass, that's the same as a recoil correction, just terms that go as the ratio of the electron mass to the proton mass. Those are known, and when you pull it out, you get 7 gigahertz. That's the Lamb shift. That's the one-loop Lamb shift. So this is one way of seeing the Lamb shift. It's not how it was discovered, but you get to this level here. Then you can pull out the one-loop Lamb shift, but to do that, you needed that progress in working on this non-perturbative function that I just described to you. And at that point, there's still a discrepancy. It's smaller, but you've still got a megahertz of discrepancy. Now that megahertz is partly the proton size, and let me introduce that now. We used to think the proton was 0.88 Fermi in radius, which would correspond to about a megahertz displacement. But recently, I'm sure you have all heard that muonic hydrogen experiments indicate a smaller radius, and there would be a difference of about 100 kilohertz. Okay, so that's in this digit here, this 6. Okay, but there's also other physics present that has to be understood before we start talking about protons, and that's the two-loop Lamb shift. And there's a great amount of energy going on in working on these two-loop diagrams with Dirac Coulomb propagators, this harder version. Normally, two-loop diagrams are not that bad, but with Dirac Coulomb propagators, they are hard to do. I wanted to mention, since this was done in Sid's theory group in 1970 by Appelquist and Brodsky, they did the first correct calculation of the first term in a Z-alpha expansion. And that actually removed a discrepancy that was bothering people at the time, and found this value of 0.53. This is actually, it's been done analytically since, and this is just the first 6 digits of an analytic expression. Now, a really surprising thing happened some time ago. The Polish physicist Krzysztof Bohutski calculated the first binding correction. So this is just like a Taylor expansion, and found this gigantic coefficient. It's really very strange to get these really large numbers. And even at z is equal to 1, this leads to a 27% effect. So it's something that is really surprising and indicates that you really have to do this thing with one of these non-perturbative approaches, though people also were doing the Taylor expansion approach. And in St. Petersburg, Yorokin and Shabayev are a couple of physicists who do this kind of calculation. Very, very challenging. Okay, so let me show you how the two loops work. Here's just a quick recap. We started with the 1s, 2s measurement, took out Dirac, the basic energies, then took out the first radiative correction to get down to this number here. And if you just stopped with what Appelquist and Brodsky did, you'd say that that this has to be attributed to proton size. And there's some other small QED effects I won't bore you with, but this would be the proton size. But the binding correction changes that by quite a bit, so it's really important. That's just the first order binding correction. So it's quite important to do the two-loop calculation. It's kind of amazing that a non-perturbative approach of such a small diagram is necessary. However, before I go to tell you about the consequences for the proton size, let me just observe that this action is happening at this digit here, there, the 1 in the 187 we're working on. But you'll notice there are 3, 6, 9, 10 digits of this thing that just are non-controversial. Those are just going to stay. So the Rydberg is good to 10 digits. There's interesting stuff that goes on beyond. But once you have the Rydberg good to 10 digits, you can get a very, very good recoil value of alpha from that equation I showed you earlier. So let me now go to the heart of what I wanted to talk about, which is G minus 2. just 1 month ago, Kinoshida's group, first author Aoyama, came out with a paper with the latest, so let me give you that. They used this value of alpha inverse, 1/137, with all those digits, that is now good to 0.622 parts per billion. And again, I want to emphasize an awful lot of QED theory is needed to make sure that you're good to that accuracy. We really have had to understand some of these QED effects very accurately. But we have, and so we have this very accurate value of alpha. We can put it into the alpha over 2 pi in the Schwinger formula, and then the other value, the higher order terms, you don't need to know alpha so accurately. And you get this number here. So it agrees extremely well with what Gabrielsi found, but it actually, for the first time in some years, there's a slight discrepancy. For many of the past years, these two numbers have been consistent. But because Kinoshida's group found a relatively large five-loop coefficient, I think it was 7 point something, normally they're of order 1, and also alpha inverse changed a little bit because of experiments. This is the first time that these guys have been different enough so that this tiny, tiny little discrepancy, which doesn't mean anything because it's just less than 2 sigma, but it's still the first sign that there might be some new physics coming from G-2. And the only reason that we can do this is that we've got a value of the fine structure constant from QED theory that's of an accuracy that is approaching what Gabrielsi has found. So for me, this is kind of the essence of doing precision physics. You're looking for a tiny discrepancy. Maybe there's something there, maybe not, but at least it's, there's a hint. Turning to the proton size, I should mention that this is kind of a bad, using these large intervals. By large, I mean n, the principal quantum number has changed. The problem is that you don't even see the Lamb shift until you're about a part per million of the basic effect. And the proton is down another 6 orders of magnitude. So it's kind of an awkward way to get the proton. But you can do it. And when you do it, you get the number that indicates 0.88 Fermi, roughly. There's an experiment ongoing that I really hope is finished soon by Eric Hessels in York University. And he's trying to get just the basic Lamb shift, the original 2s, 2p 1/2 splitting, to 2 kilohertz. The difference that I just showed you for the 2 proton sizes corresponds to 12 kilohertz. So he should be able to clearly say, favor one size or the other or find yet another one. So that's an important thing to look out for. But of course, the simplest theory, the simplest and most accurate system is muonic hydrogen, which there's hardly any theory to it. There's no controversy whatsoever. We've got total control of everything except for some proton effects that we're pretty sure are not important. And it indicates a smaller radius. There was a recent, well, not that recent, this was actually reported at that Warsaw meeting, that somebody did one of the large intervals. In this case, instead of 1s, 2s, 2s to 4p, did the experiment very carefully and seemed to, and found a smaller proton radius. But there are more recent measurements that appear to favor the larger ones. So it's up in the air. It's something that just needs more investigation, but it would be really nice if the Lamb shift were done. Okay, now a second main thing that I wanted to emphasize, and I apologize for borrowing Bert's comment, but it's just so germane, is he just, in this case, talking about particle physics, was talking, just said this, that as head of the Slack theory group, he brought a whole host of theoretical physicists who began creating the present picture we have of the structure of matter. But along with that, that environment that he created led to work that was very important for my field of quantum electrodynamics at a very small energy scale, but still that influence, that beneficial aura that kind of emanated from him passed on. to work by Caswell and Lepage. And in the 1978 talk that I've been emphasizing, he told Schwinger that about recent progress in this case was hyperfine splitting, ground state hyperfine splitting in muonium, which I won't go into, but the nice thing is that he was able to say our theory group that Caswell and Lepage had done a certain calculations. And this led to the field of NRQED shortly after. Caswell and Lepage are responsible for establishing this effective field theory, and it just had enormous effect in quantum electrodynamics. And let me illustrate that with many electron atoms. And the simplest one, of course, being helium. And the atoms that I'm showing, helium, lithium, beryllium, and to an extent, even up to carbon, people have found fairly recently very useful basis sets that allow you to solve the non-relativistic Schrodinger equation for a many electron system with just enough accuracy that 16 digits easily for helium. And that has allowed very accurate calculations to be carried out. Here's the ground state energy non-relativistically. And I'd better close at this point here, even though I've got more to say. But this has been applied recently by Bohutsky and Yorokin to helium fine structure. Again, a subject that Drell was speaking of. And you can use helium fine structure if you have a sufficiently accurate experiment. And there it is. It's good. It's 4 parts per billion. But unfortunately, it was an enormous amount of effort even to get this 31 part per billion, because the theory is incredibly difficult. Nevertheless, it has been carried out to a certain order, m alpha to the 7th. The next order was discussed at this Warsaw meeting, and even these two gentlemen were there, but even they quailed at the idea of carrying out that next level. So the story for helium fine structure is consistent, but we really can't go much beyond that. And I've gone a half an hour, so so let me stop at this point here. Any questions for the speaker?
This microphone system here.
So eventually the perturbation series for QED quantities like the G-2 should grow factorially and not converge. Can you see any of that growth yet when you've gotten to 5 loops, do you know?
Well, the coefficient up before 5, it was just everything was order 1, and then there was this striking 7 that came out in 5th order. So maybe that's a hint of it, of something beginning to go
I guess
off.
with just one term, it's hard to be more quantitative than that, though, huh? Yeah. 6 loops.
That's what Sid wanted. He didn't want to have to deal with this sort of thing. He wanted Schwinger to just tell him what the function was.
Thank you very much.
Sure.
So the next speaker is David Hertzog from the University of Washington. David is a longtime campaigner in particle physics, most recently one of the initial participants in the Brookhaven G-2 experiment, and now the co-spokesman of that experiment remounted at Fermilab. It's interesting that the two moments of leptons, the magnetic moment of the electron and the electric dipole moment, the magnetic moment of the muon and the electric dipole moment of the electron have now been viewed as gateways to new physics, and we'll hear about those in succession. So, David, you'll tell us about the muon. Thank you very much.
Thank you. Well, it's an incredible honor to be asked to represent this experiment in this symposium, so I want to thank the organizers for including me on it. I'll tell you about that picture in a moment. Let me set up briefly the story for today in this picture and then back up from there. But basically, about 10, 12 years ago or so, the Brookhaven experiment finished this measurement of the anomalous magnetic moment of the muon to a precision of about 540 parts per billion. And at the time when you compared it to the complete standard model evaluation, it was 2 and something sigma away, and it was kind of interesting at that level, but it was always kind of honorable mention in terms of physics. And along the way, I had the feeling, and others had the feeling, like we can't just leave it like that. We probably ought to try to clear this up, whether we want to do Groundhog Day and do the same experiment again. But so we did design and have approved a kind of experiment that will take it to the next level, which is the goal of the experiment I'll talk about now that's actually beginning to run, will reduce this uncertainty by a factor of 4. Along the way, of course, theory has improved, and most of the error bars here are related to a part of the contribution which we did not hear about in the previous talk, the hadronic contribution, and I will mention what that is and a little bit of progress on that. So we expect with a couple of modern techniques that the overall theory will go down by about a factor 2. This includes some of the things I'll mention. Anyway, that's the story of today, and let's back up from there. Now, of course, I get to be early in this thing, so I get to show the picture of the books. My grad school thought I didn't know what I was doing, but I had to buy these books at the time. They were expensive. And I thought to myself, I don't know what these are about, but they really look like they're interesting. And I still covet these, as probably many of you do in terms of our thing. There's another book I covet right now. This is the 700-page book on the anomalous magnetic moment of the muon by Jägerlander, and this is just full of all the details of the theory in particular that just relates to this one experiment, which is, of course, many-generation experiment going back decades and decades. It's a lovely thing. Now, I don't want to say anything in an audience like this that's too trivial, but of course you start with a picture of the muon in an electromagnetic field and the Dirac equation, which was lovely because it predicted antiparticles, it predicted G equals 2, and for spin 1/2 particles, there's a structure there that allows a Pauli interaction term, so it allows a deviation from G from 2, and my talk is about a deviation from G from 2. We give you the 2. Of course, when it started off, the G looked like 2, but then people looked at the simple elementary spin 1/2 particles called the proton and the neutron, and it wasn't anywhere near 2. In fact, what that meant, in fact, why should the neutron have anything at all? You might ask yourself that question, but it started to show the following, that there is some kind of substructure in those things. And so the harbinger of the quark model, in a way, was the large magnetic moments of the baryon. Something I actually did as a thesis experiment was one of the nucleons as well. Now, on the other hand, if we could just write the relationship between the anomaly and G, just to get it, G minus 2 over 2 is the anomaly. And what we heard in the earlier talk, of course, this lovely picture, which is on the tombstone of Schwinger and everything, is this leading order term with this virtual photon across it. Just to put into a simple way, rather than all these digits, which I was scribbling down in the first talk myself, the first term is about 1 part in 800, so it gives you an idea. So the deviation had to be pretty small. The experiments had to be kind of precise to even notice that. And in 1947, these deviations at this level were just beginning to percolate up in an experiment like that. And that's what led, of course, to the development of quantum electrodynamics. So I said to myself, in the inventory of being involved in this for many, many decades myself now, I don't really remember Sidney Drell being involved in any of the particular calculations that I was quoting, so I dug up a little bit, and I found this amazing paper, which was alluded to by Jonathan. It's a very nice long paper, anomalous magnetic moment, electron, muon, and nucleon with Sid Drell. And the whole first paragraph is a lovely tour de force going back to El Salve conference in '61, where Feynman put out the challenge that somebody, he says, look, we're calculating terms like blind men, with no physical understanding. We don't even know why the sign is positive. And I remember trying to figure this out myself one time, just intuitively, classically, if you want even. And had my own version of that. So it was very cute. This paper, in fact, this paper is our answer to the challenge. I won't go into that paper. The learned folk in this room are better at talking about the dispersion theory involved in that. Of course, this is cute. Jonathan mentioned this is literally 3 weeks ago that Kinoshita is still cranking away on these terms. This is those 10th order diagrams, and here's the projection of those digits. So let's just agree that at 12,672 diagrams, we are in fact for the muon well beyond this having any influence in the precision. It's lovely, it's fun, we include it, but we're not sensitive at that level. In fact, what we are sensitive at is this electroweak level. So one of the things about being a muon and not an electron in this problem is by being a couple hundred times heavier than the electron, and the way these things typically go with the square, we're 43,000 times more sensitive to heavy physics exchanges. So the W diagram, new physics diagrams, is much better to explore with a muon. So in fact, this was calculated. This is about a 1,300 ppb effect. Remember, the experiment I'm trying to measure is 140, so it's almost 10 times larger than the experiment, just the effect of these kind of exchanges. So this is, becomes the monkey in the room problem. It seems simple. I always like these pictures of vacuum polarization, but when you turn them into hadronic vacuum polarization, they become non-perturbative problems. So you ask yourself, how do you do that? So how do you do that calculation? That's no longer something you can just crank through. So you measure that in a very different way, which is kind of cute. So you take a scissors, you cut the diagram like this with the scissors, you're left with this little piece. This is literally PowerPoint scissor cutting. You turn the thing like that, you have a photon to pi, and you ask yourself, what could introduce that? And you can do E plus E minus annihilation. So then you basically measure those E plus E minus hadronic contributions all the way across all energies, use the dispersion relation, we all know this R ratio business, and this gives you back the hadronic leading order contribution to the muon anomaly. In fact, right here at SLAC, some of the most beautiful and significant measurements. This is just one of many, many cross-section measurements. If you notice, this goes 0.6 to 2 GeV. These are absolute cross-sections by Babar and all the pion channels. They did many other channels beyond that, as have many other groups around the world. And the ticket here is to add all of this up with careful bookkeeping and good systematics, and that gives the number that is dominating the error bar that you saw on the second slide of the presentation. They get better and better and better because this is an ongoing exercise with improvements, including the lattice. When people had now three-ish sort of standard deviation problems with difference between G minus 2 of the muon and the theory, there's two kinds of people. One that think this is exciting and one that thinks it's wrong. And if you think it's wrong, there's two ways to think it's wrong, and almost everybody thinks the theory is wrong. The experimentalists are thinking it could be the experiment, but the theorists are thinking it could be hadronic light by light, because this mess of a diagram here isn't something that you can get out of data, although new ideas are in play to do that. But this is model-based, and so the distribution of the models had an uncertainty of the order of, sort of 26 like this in some units. And the latest thing is there's been a campaign led by others, with Tom Bloom and others, to do it on the lattice, and they've been remarkable. A year ago already, the statistical result of this diagram being done on the lattice with all the normal things, physical pion masses, large boxes, all those kinds of things, disconnected loops, all the kind of magic that you never believed would happen a decade ago, already is a factor of 2 smaller than the best model. And they spent the last year working through the systematics of this. So I expect sometime in the next year that they will have basically produced this number in a trustable way. I think it's one of the most important numbers the lattice will come up with, because we have no counterpart to measure it. So then it's all bookkeeping. People add these things up, and you add these things up with all these diagrams, and that's where you get about 3.5 standard deviations these days. So what could it mean if the experiment is not equal to theory at sort of greater than 5 sigma? Of course, the design is that we should be 5, 7, 9 sigma if we don't move. Things will move, so we don't know where they would go. And with this kind of typical nice argument by Chinecki and Marciano, where you can connect the equivalent of the corrections to the muon mass kind of diagram like that, the self-energy correction, to the magnetic moment corrections, then they have sort of the same kind of structure, where out in front is this coefficient, and this coefficient would be what you might call a coupling constant here. So if it's of order 1, it's kind of radiative muon mass. I think this is a little bit like the same thing as saying, does the muon have does it have substructure way out at the multi-TeV region? That's probably been ruled out. I don't know, maybe Ann will mention it does, what we know about that, I don't know. If it's of order kind of an alpha over 2 pi, typical electromagnetic correction, then it would be down here. So what you see here is the mass of some exchange, which goes out to 2 TeV right there. And this yellow band right now is the deviation from the standard model to the current theory, and the blue would be maybe where you might be later. And so that looks like they'll be ruled out, because there's a couple hundred MeV or so, and Lep and other places would have seen that. And so this nice swath band in between here is when you have something like an enhancement factor, like you get in supersymmetry when you get tangent beta and multiplying, or some other models that have enhancement factors to be in there. And that's why people like this. This is a while ago. That people liked this idea because it looked like it fit in things we wanted to have be true. I've become completely agnostic to this. Because if you start to ask yourself, what's the situation kind of recently? You could go, well, you know, a year or so ago there was this. I wrote this on the beach in Oregon. I waited about 30 seconds for that, and that was that. Supersymmetry, we know, at least in the hadronic side, it's really, you know, not there at a high level in terms of mass scale that corresponded to that. Could be hiding under a rock because we're dealing with leptons here. We like the idea that there was a possible dark photon. This is a G-2 band. This is a coupling of a so-called dark photon, but then these experiments, Babar and others, have sort of wiped that space out. And so this is the way it feels for me right now. G-2 is kind of walking out there as one of the singular things in a very nervous sense. It makes us return to saying our job is to do the experiment correctly. So this is a cast of characters that's working on a new experiment. The interesting thing about this, and it's really true what's written here, all of these people that are working on this come from particle, nuclear, atomic, optical accelerator, and theory communities. There's a very eclectic mix, and all of these people are running shifts. So you can imagine the interesting language in this experiment where people are unfamiliar with the terms from another subfield and so on. But it's what's needed because the experiment is so broad and interesting in that way. We're all measuring one thing, G-2. So how's it done? Basically, you bring in a beam of polarized muons into this magnet. This is a dipole magnet. It's the same one that was used by Brookhaven. They're polarized, and because G is not equal to 2, the spin precesses ever so slightly ahead of the momentum vector. And so the difference between those two vectors is called the anomalous precession frequency, and this you can get out of Jackson. And if you just concentrate on the first terms, you see that the precession is proportional to the magnetic field times the anomaly. But there's a couple of other terms because in order to keep particles in that ring, you need electric fields, electric quadrupoles. It's a giant penning trap. And so there's a term there for the motional magnetic field. When you go flying through the electric field, looks like a magnetic field. When you go through the electric field, when you go flying through the electric quadrupoles, it looks like a magnetic field, which would then be like that. But what was discovered in the mid-70s by the third CERN experiment was if you could tune the momentum of the storage ring to a value to make this coefficient out front equal to 0, it's called the magic momentum at 3.094 GeV over C. It's not an option kind of a thing. Then this term goes away, apart from a correction. If you're interested at the end, I'll show you the correction for those muons who are a little bit higher or a little bit lower. And this term here is when in case there would be a muon electric dipole moment. So in fact, we measure parasitically a limit on the electric dipole moment by a couple of techniques, but for now, we can assume that that's 0 and doesn't perturb things. So all you really have to do in an experiment like that is you measure the precession frequency, that's one group of people, you measure the field, that's another group of people, and then you do long division. And when you do long division, you get out A. And that's how it's done, and that's how it's blinded and things of that sort. So a formal way to write this is more like the following. Here's A mu written as a number of ratios to put things in the right way. So first of all, we do borrow the number from G-2 just to set this of the electron, but that's a trivial uncertainty compared to what we're doing. We get some numbers for fundamental constants from muonium hyperfine spectroscopy, which is also being redone at JPark. And then we measure two numbers. We measure that precession frequency and the field. And the little tilde in there, I'll mention in a moment what the tilde stands for. So what's reported in the literature is that ratio. So if you want to fiddle around later in life by these changing or these changing, the data is in fact updated. So the trick in life is to be the last people to measure something. Now, if you want to do a much better measurement, 4 times better in precision or so, we need 21 times the data set that Brookhaven. That's a non-trivial amount more data, as those of you who know these kind of experiments. That's 20 times more data to get to 100 parts per billion on the statistics. We need to improve the magnetic field was really good and small then, and it's non-uniform. We have to improve that a factor of 3 to get to 70 parts per billion on the integrated magnetic field around this many 40-meter ring. And you have to improve all the precession frequency measurements under an incredibly high rate that we're expecting, the detectors have to perform in a way that's unprecedented in a level. So this is how the gadget works. This is at Fermilab. This is a top-down picture, and if you're a high-energy person, this is the Tevatron back here. So these are the little intermediate machines, and this is where they used to put the antiprotons. We've stolen that ring. We've stolen a lot of stuff and make a muon campus. So you get HEV protons. They zip around this thing. They break them into 4 little pieces in some funky little way that looks literally like that. That's 120 nanoseconds, and it looks like a building. Extract one by one. They smack into what was the old antiproton target. They make now 3 GeV, 3.1 GeV pions there. They go 300 meters. They decay. Then we whip them around this ring 4 times to get rid of all the pions. And then we catch them in the storage ring right here. That chain is an incredibly inefficient chain, but that's what it is. And they're essentially 95% polarized without a background particle. A huge difference between this experimental approach and Brookhaven, where the distance was 100 meters before and the background of pions was 1-to-1 to muons. I'll skip some other stuff on that. We did like the magnet. It was an amazing thing. So with a lot of fanfare, we brought it to Fermilab and had a big party. And then you have to build what I told the program advisory committee one time in error. I made a big error. I said, then we have to put Humpty Dumpty back together again. I thought that was really cute. And then my collaborators reminded me that all the king's horses and all the king's men couldn't do that. And then for 3 or 4 years, I was pretty much panicking. But we did build it. And it is looking like that right now. And let me show you some cute things about the magnet, because it's just so cute. Basically, this is a slice, a side view of that magnet. And just to know, it's not just a gadget you buy and turn on. It's built out of a lot of parts. And those parts enable you to shim that magnet to a lot of precision. So there's like 800 of these little wedges. All these poles get put in just so. These things can be moved around, so-called top hats. All the geometry of this has to be absolutely accurate. We're talking tens of microns or better for the placement of things that you can only pick up with a crane. So you can see you have to wear hard hats and lift stuff like that. So let me just show you how you do that. So you put the thing together, and you're going to use now proton NMR. So you're looking for the free induction decay of a proton spinning in a magnetic field to measure locally what the magnetic field is. And so this is a good one. And this was like, and these probes are just millimeters in size. And this is if there's a gradient, right, a tough gradient, then you'd see something that looks kind of ugly like that. And you'd like things more like that. And now this little picture here, imagine you have a bus. A little bus is about this big, and it has 25 of these probes on it. And you drive this bus around the ring, and you measure at any given location the free induction decay to map the ring. So it looks kind of like this. So here it is driving around the ring. And this is what we are doing for a year until we can get the thing going. So we're measuring the here's the average dipole field, and then as you see, there are good places and bad places as you go past locations where there are bumps and so on and so forth between steel pieces. So now this laid it out, the average field is a function of 360 degrees, and this is what Brookhaven had in blue, and if we spent an enormous time building this thing, this is how good we did in red, which wasn't so good. We were hoping we would do much, much better, but it was about the same as Brookhaven when they started. So then you start moving those big pieces around, these red things, and so this is literally months. This is going to be a year right now, this plot. And you start to see the thing get better and better and better and better, and you get to a point where you just can't do anything else because the wavelength of the field for something this large perturbs more than this local structure. So then you start to use slightly other things. These little wedges are about this big, and they have a wavelength which is a little smaller, and you have to calculate what should you do. You have hundreds of these to move in and out and so on. So then you do the campaign for a couple of months of moving those. You start to get a little bit better. When it drops down, that's just you turn the current down in the field, by the way. You can move the whole thing down like that. And now it looks like you're almost at the same place, but you didn't really get any better, and you're kind of run out of tools. That's the end of the tool set. So you have to invent a new tool, and the new tool is the following. If the field looks bumpy like this and you like it smooth, imagine if you put little bits of iron, all tiny, measured at tiny little strips of iron, all custom made to be the inverse of this field, and you make plates of these like that, and glue them on the top and bottom all the way around. And so at our lab, we cut about 10,000 of these little pieces. And these 10,000 pieces, 8,000 of which are used to form these inverse patterns. And now watch what happens. This is all new stuff and now we're testing it, and this idea seems to work. And boom, suddenly it's 3 times better than Brookhaven ever got by this technique. So that's where we are right now on this, and I'll just leave it at that to let you know that in each and every case we're spending a tremendous amount of time trying to get somewhere. The next step is you got to catch the decays. And so here's a ring, and about 24 places around the ring, you stick a detector, some kind of a detector like a calorimeter has to be real fast, and it has to stick it into the magnet, which is 1.45 Tesla, measure things accurately with very high speed at a very high rate, while things change by about 4 orders of magnitude every time you fill the ring and empty the ring and fill the ring and empty the ring. So we've done that. This is what happens when an electron hits the thing. You measure it like that. If it has a certain energy, you keep it. What's the decision point? Well, at 3 GeV, the Michel spectrum, you remember the decay Michel spectrum, is boosted to 3 GeV for the muon, for the decay electron. And that's from 0 to 1 here. That's what that means. And then if you plot the number of electrons, that's green. So it does go down as a function of energy, but the symmetry goes up. And what matters in polarization experiments and so on is the product of Na squared, the figure of merit. So if you make an energy cut about here, you really get the information you want right there, and you end up with this famous plot you've probably seen, which has all what we call the wiggle plot like that. And the wiggle plot is statistically going with Na squared like that. So you want a lot of events of high energy. And to do that, you want to measure them very cleanly and sort them very nicely. So why does it wiggle? Well, as the muon spins around, this is what really happens is the detector sees a very different energy spectrum back and forth because of the boost. So you're spinning this muon around, and remember the parity violation sends the higher energy electrons in the direction of the spin. So as the spin is going around like that, and then you translate that with a boost of about gamma of 29, you end up with this oscillating kind of energy spectrum, and that's what makes the cut. So it's really a cut in energy that we're making that carries that information. This is a little plug for a laboratory called SLAC, because this is where I did all the work to develop these. And in the old days, we had a monolithic detector just read out on the side. But to get to another level, we needed a really modern, fast, and subdivided detector. So we built it out of these Trenkov crystals, lead fluoride crystals, like that. And then to operate in a magnetic field instead of a photomultiplier tube, we developed a silicon photomultiplier sort of idea, this thing here. And these are papers that we've published on this stuff. All this work was done at SLAC thanks to the hosting of Karsten Hasten here and his team. And this is actually from SLAC, these 2 pictures. Here's 2 electrons at 3 GeV separated by 4.6 nanoseconds, which we can easily resolve. And that is right at the systematic level that matters. It's really amazing. And, you know, I told you there are optics people in this experiment. This is a part of an optics table, the distribution. In order to keep the gain of these detectors at 10 to the minus 4 in an hour, something like that, is really a factor beyond what anyone would ever do. There's an incredibly elaborate laser system which flashes and monitors every detector constantly. It's been running for a long time that the Italian groups have built that are amazing. And so the thing looks like this, and so you get it all built, and you say, well, how am I going to make it work? You know, and so you're kind of christening it, and everyone's happy. But I can tell you this has been months of work to try to bring the beam up and everything else. Last June, the first time you store muons, they do precess. They still do. And everybody signs the paper, and you think this is great. We put it in the counting room. This is the 24 detectors. They all seem to have the right energy spectrum and compared to theory, which is one of these, like they call atlas plots because they're yellow or something. And then this is just a couple days ago where basically this is still lousy data, but lousy data with 5 parts per million precision isn't too bad. In the sense it's lousy because we haven't really established the magnetic field uniformity and measured it. We're still mapping and things like that, but this is coming out every day. We're getting something of this order, and we're still about a factor of 20 or so lower in the rate that we're going to be collecting data, which is just, if you do the math, we probably get to June we get about 3 Brookhavens by June or so. And just to blow up, this is still the same data in the fit, so you could just see how pretty this stuff is. You got it. No problem at all. And actually, this is a plot too, just like yesterday plot too, which is interesting in the following sense. This is time, like 20 microseconds to 80, doesn't matter. And these stripes here are G-2. This is the energy of the decay electron. And down here, these little yellow things, we've never seen this before, but with new detectors that allow you to look at thresholds down to 20 or 30 MeV instead of just 3 GeV, these little spotlights represent what's called coherent betatron oscillation. So the beam breathes back and forth, and if it hits a collimator, it pops out, muon goes through the detectors and gives a little flash. One of the most important systematics. We can just actually see it here, so we know exactly what's going on. And then we built this a couple of tracker systems. This is you know what GoPro is, right? So we have a trolley that drives around inside our vacuum and measures the field, but we put a GoPro camera on it, so now we can see the stuff that's you don't get to see otherwise. These are straw tracker chambers in the vacuum as you drive by. There are 2 of them. And they do tracebacks to give the image of the beam, which we need to get the systematics. And this is actually an image of the beam from December, right in the right place, and it's the size of the beam. And here's a typical track that goes into a calorimeter of some kind of a beam like that. So that stuff is working, and that's totally new for this experiment too, to give us a handle on some more stuff. Since I have 1 minute, I'll just tease you with 2 things that show you that there's other orders of complexity to this experiment. This is the electric quadrupoles, which keep the beam in there. So this is a positive plate, negative, negative, and that's the electric field lines. As this is the distribution of the muons, I very carefully made it exactly the same size. So if you're a magic muon, then you're exactly at that right energy. That's the gamma right here. If you were one of these perfect muons, you go right down the middle and it's fine. But if you're a higher momentum or lower momentum muon, you're on to the one side or the other. So if you're one side or the other, then you pick up a term, and there's no cancellation of sign in the way this works out. And basically, it ends up being about a half a part per million effect. So you realize we have to do this really, really well, because this is much larger than our uncertainty. And another one of these is, well, actually, because of vertical betatron oscillation, I'll exaggerate here, but the muon is diving and swimming like a dolphin through this field. And you have to carefully take into account the fact that it's not exactly perpendicular. And that's a tiny effect, but we have to map all that stuff as well. So these are the activities which involve a lot of the people in the collaboration quite a bit right now in what we call beam dynamics. So we have detectors, beam dynamics, magnetic fields, optics, and the theory stuff earlier mentioned. So what's the outlook on this? Well, by the way, here's Rick Perry just on Tuesday checking out the experiment. He came through Fermilab. It was really nice. He's learning about Lenz's law right there, because you basically put a piece in this field, you could put a piece of metal and it just falls over slowly. He had a lot of fun. And so, we're looking for new physics, right? We're looking for new physics. Right now, the LHC is in what I call a bit of a lull. I'm a little bit nervous because I was really hoping they would set the scale for something. But so far, the TeV scale at least isn't popping out as robustly as we had been hoping. And now, in the field that I'm in, which is low energy precision searches for standard, beyond the standard model, there are things like electric dipole moment searches. There's charged lepton flavor violation experiments. Some of you are involved in those. Double beta decay programs, beta decays of nuclei, neutrons, parity violating electron scattering experiments, and G-2, among others, that are all searching kind of indirectly for physics beyond the standard model. So in about a year or so, year and a half, we hope to at least let people know how this is turning out. And we should have our first number at least Brookhaven level, or a couple times better than Brookhaven, before we get to this final stage. And that alone, by the way, would be enough to let us know. If it's in the same place, that would push it over 5 sigma. Thank you very much for your attention.
Better. Hi. Is it understood why the iron foils were needed to even recreate the alignment that you had at Brookhaven? Was it just jostling from the transport or something else?
No. The little tiny iron, we got to the same level as Brookhaven using the same things that Brookhaven did. But with these tiny things, we wanted to go better. So if you think about the magnetic field as having, you put in a piece of iron or something, it has a little bit of a wavelength that you calculate. How far away does it perturb the field? When the substructures become kind of short like that, jagged, then you need just smaller and smaller pieces. And also, I didn't exactly explain, but in the radial direction, there are layers as well, which changed. And none of the tools that existed in the Brookhaven allowed that radial change.
I see.
One other thing I didn't mention is there are hundreds of surface coils right now that we dial as well to figure out, we can move the average radial field and we can tune out the multiple moments. So we have one more campaign which is ongoing now, which is dynamic and not static.
If I may, you didn't mention mu plus versus mu minus. Is there any possibility of doing both?
Yeah, absolutely. And the only problem with that in this configuration is the cross-section for pi minus production from an HeV proton versus a pi plus is down by about a factor 2.7. So until we can get a really significant flux through here and what we call a new inflector, which opens the door into the magnet, which is being constructed, we don't have enough flux to make that attractive. There's also some vacuum questions which are highly technical, but let's assume we can solve them if we can solve the other. The purpose of that doesn't have any particular systematic in the equation, but it's emotional. People like the idea of doing mu-minus because it's emotional. And we did do that at Brookhaven because there didn't have a cross-section problem because the proton beam there was 24 GeV.
Thank you very much.
Thank you. You can have this too.
So we now move from the electromagnetic properties of the muon to the electromagnetic properties of the electron. David DeMille is a professor at Yale University. He's well known for his studies of atomic parity violation and study of the fundamental interactions using atomic physics tools. In the past few years, there's been a major effort in the atomic physics community to search for time reversal violation in atoms. There's a large collaboration, probably the largest one in the history of atomic physics, called the ACME collaboration, which has been after the electric dipole moment of the electron. David is a prominent member of that collaboration, and he'll tell us about it now.
Great. Well, thanks for the introduction, Michael, and I'd like to thank Michael and the other organizers for the invitation. It's a tremendous honor to be here. I never had the pleasure of meeting Sid Drell, and like Dave Hertzog, I actually sort of went through the literature trying to see if Sid had ever worked on anything related to the electric dipole moment of the electron, and nothing other than his work on the magnetic dipole moment of the electron. I do have a sort of third-order connection to Sid Drell through Persis. She and I are academic siblings, having both gotten our PhDs with Gene Cummins at Berkeley. But at any rate, in some sense, I think I'm here as the entertainment, so I'll hope I can entertain you and tell you about something completely different, which, as Michael said, is experiments that we're doing to look for the electric dipole moment of the electron. So I'll talk a little bit about why we're doing this, what the connection is to particle physics, a little about the concept of how to detect an electric dipole moment, then some brief explanation of our experiment called ACME that gives the best upper bound on the electron's EDM so far, and talk a little about what it means and what the future of this kind of study is. So the place to begin is to understand that any particle, an electron or any particle with a quantized spin, if it has an electric dipole moment along its spin axis, then that is evidence of violation of time reversal symmetry. So here's a sort of cartoonish picture of an electron with a dipole moment attached to its spin axis. And if you take this cartoonish picture and apply a time reversal transformation, of course the spin direction changes sign, but the electric dipole moment, which is a static charge distribution, doesn't. So if all electrons have a dipole moment in a given direction relative to their spin, time reversal symmetry is broken. And of course, in quantum field theory, CPT is a good symmetry, so T violation is equivalent to CP violation. So this means we're able to study CP violation without having to have access to any antimatter particles, just by looking at ordinary electrons. And just as an aside, this also violates parity symmetry, but that's sort of tangential to our story. So Of course, CP violation has nothing to do with quantum electrodynamics, but it does exist in the standard model. What's sort of remarkable is even though there's order unity CP violating phase in the CKM matrix of the standard model, it leads to non-zero but extraordinarily small electric dipole moments of the electron and other fundamental particles. And that's essentially due to the way that the CP violation enters the standard model only via the quark mixing matrix. And it turns out that in the standard model, you actually need a 4-loop Feynman diagram to generate a non-zero electric dipole moment of the electron. And in addition, through something that's basically the equivalent of the Jim mechanism well known from kaon physics, there's an enormous cancellation when you sum over all these 4-loop diagrams. So the bottom line is that the standard model prediction for the electron's electric dipole moment, while it's not zero, is roughly 10 orders of magnitude below current experimental sensitivities, and really serves as effectively a zero background in our attempt to look for this and look for new physics by looking for the electron's EDM. By contrast, in most particle theory models that include new physics beyond the standard model, it's much easier to induce an electric dipole moment. So here's a sort of cartoonist version of a very simple supersymmetric model where a simple 1-loop Feynman diagram can induce an electric dipole moment as long as there's some mechanism for violating CP in the theory. But in most theories beyond the standard model, introducing the new degrees of freedom associated with new particles generally turns on new sources of CP violation. For example, in supersymmetric models, these tend to occur, new CP violating phases occur from the SUSY breaking mechanisms. So I emphasize supersymmetry, of course, because there's so much of the theoretical literature over the last few decades has been written in the framework of supersymmetry, but there's nothing special about supersymmetry. You can even do a very simple sort of dimensional estimate for the size of an electric dipole moment, much like the anomalous magnetic moment of the muon that we heard about. It arises only due to radiative corrections. You can write a generic Feynman diagram with a loop. And what do you need to estimate the electric dipole moment from a diagram like this? Well, because it's like a radiative correction, it has to have size that's given by the natural scale, which is the magnetic moment of the electron in sensible units where electric and magnetic moments have the same dimensions. It must depend on the coupling strength of some new particle that appears in this loop in much the same way that the fine structure constant appears in the expression for the anomalous magnetic moment of the electron. Just because of the propagator of this heavy particle, in order to get the dimensions right, there has to be a factor of electron mass over new particle mass squared. And then it depends on the size of the CP violating phase, usually parameterized by the sign of that phase. So, and what I've shown here is a simple 1-loop diagram, but if you have multi-loop diagrams, typically from a dimensional point of view, the only thing that changes is that this loop factor gets multiplied or raised to the power of the number of loops. So if you put in some fairly natural assumptions for where new physics should appear, coupling strengths of order electromagnetic couplings, not weaker than that, CP violating phases of order unity, just like the one CP violating phase that we know in the standard model to be non-zero, and new physics appearing at the mass of around 1 TeV, this dimensional estimate tells you that you would get an electric dipole moment which is about 30 times larger than the current limit from the experiment that I'll tell you about. So this is just a hand-waving dimensional way to see that our experiment is already probing well above the TeV scale in any model where there's new sources of CP violation. So as I dive into telling you how we do the experiment, I want to just emphasize how small the effect that we're looking for is. So let's imagine, this is a sort of artist's conception of what the cloud of virtual particles around an electron would look like if it had an electric dipole moment. So just to get a sense of scale, there's a natural scale for the size of radiative corrections associated with the magnetic moment of the electron that's just given by the the anomalous magnetic moment, that corresponds to about 10 to the minus 13 centimeters, essentially the classical electron radius. So if you scale this up to the size of the Earth, and then compare this to the size of the charge displacement that we would have seen for the electric dipole moment in the previous round of our experiment, that would correspond to taking a slice about 20 nanometers thick off the northern hemisphere of the Earth and pasting it on the southern hemisphere. So these are incredibly tiny effects. And because of that, I'll spend some time talking about how we go about making sure that we're not subject to systematic errors that can fool us into thinking we're seeing an EDM when it's not really there. So the basic concept for doing these measurements is actually quite simple. You start with some electrons. In our experiment, like most in the field, we use some polarized laser light, transfer the polarization of the laser light into polarization of the electron spins. Let's say, for sake of argument, we polarize them sideways, so they're in a superposition of spin up and spin down. For technical reasons, we tend to apply a magnetic field. That exerts a torque on the magnetic moment of the electron and causes the spin to start precessing around the field at a frequency proportional to the magnetic moment and times the magnetic field. Equivalently, you can think of this as a Zeeman splitting between spin up and spin down. And in some sense, what we're doing is making a spectroscopic measurement of this energy splitting. Then to look for the EDM, we apply an electric field parallel to the magnetic field. If the electron has an EDM, that exerts a slight additional torque, speeds up the precession frequency, equivalently causes a change in the Zeeman shift, or shifts this spectral line. Then we reverse the electric field and flip the electric field back and forth, and look for correlated changes in the precession frequency or the Zeeman splitting according to the direction of the electric field. This picture makes it easy to write down a simple figure of merit for the statistical sensitivity of an experiment like this. It's just the size of the energy shift divided by the energy resolution. If you work this all out, that means you want a big electric field to exert the largest torque on the electron. You want a long coherence time to give you good intrinsic energy resolution. And then you want good statistics. You want to have a high counting rate, and you want to integrate for as long as you can. So in our experiment, we've gone to great efforts to maximize the electric field, the counting rate, the coherence time. The total integration time in the experiment is essentially a constant of nature that's determined by how long our graduate students are willing to sit in the basement and flip the electric field back and forth as they watch the data come in. So one of the keys to our experiment has been the new techniques to apply the largest possible electric field to the electrons. And essentially, we do this by embedding our electrons inside a polar molecule, in our case, the species thorium oxide. We apply a relatively modest electric field, actually a very modest electric field in the lab, some tens of volts per centimeter. That completely polarizes this polar molecule. But then the electron, in its bound state wave function, experiences an intramolecular field which is orders of magnitude larger. The basic theory of this was worked out back in the 60s. I'm sweeping some interesting physics under the rug, but essentially the effective field that acts on the electron EDM depends on how strongly you polarize the molecule. It depends on the atomic unit of electric field, and then on alpha squared times E cubed. So we use a very heavy atom, thorium, in our molecule. If you put in the numbers here and do detailed calculations, it's been worked out that the effective field acting on the EDM, when we apply a laboratory field of tens of volts per centimeter, is about 80 gigavolts per centimeter inside the molecule. And this theory has been worked out independently by several groups. The accuracy here is below 10% now, which is plenty accurate for our purposes, unlike for muon G-2, where you need theory that's accurate to many, many digits, because we're essentially looking for anything that's non-zero. As long as this theory is better than a factor of 2, then it's good enough for our purposes. So it's worth pointing out that in order to make this work, you need the electrons in this molecule to have unpaired spins. And chemists call molecules with unpaired electron spins free radicals. Physicists usually call them horrific nightmares. This This idea of using molecules to get an enormous electric field had been known for decades, but experimental techniques to be able to take advantage of it have only become available in the last 10 years or so. So that leads me to our experiment, the ACME experiment. It's a collaboration between my group from Yale and 2 groups from Harvard. The experiment actually takes place on campus at Harvard. Here's the team of ACME students and postdocs. So in addition to me, the PIs are John Doyle and Jerry Gabriels from Harvard, a tremendous team of students and postdocs. As Michael mentioned, this was by far the biggest collaboration ever assembled in atomic physics to do these sorts of experiments. But in case you're alarmed by the size of this collaboration, you should know that only about half of the students and postdocs were actually there at any given moment in time. So, yeah. So, a key breakthrough that allowed us to do the experiment was a development in John Doyle's group of a new source of molecular beams. Here we inject molecules into a cell held at cryogenic temperature and filled with neon buffer gas. The molecules are cooled by the neon buffer gas and then ejected out into a stream that gives us a brightness of the molecular beam that's about 3 orders of magnitude larger than anything that had been previously available. So that allowed us to get better statistics than had ever been possible before. Another key development in our experiment was using this particular molecular species, thorium oxide, which no one had thought about before we started using it. You can notice in thorium oxide, its ground state, forget most of the notation, but the key point is the ground state is a singlet state. It actually has closed electron shells, which means it's chemically stable and much easier to make than a typical molecular free radical. In order to do the experiment, we, instead of using chemistry, we use lasers. So we pump the molecules into a metastable state, which is a triplet state, where there are 2 unpaired electron spins. And that allows us to use the molecules, or to make many more molecules than is possible if you try to make a free radical directly. So in our experiment, we populate this metastable triplet state where we actually do the measurement, and then we detect how the electron spins, or both polarize the electron spins and then detect how they precessed using another laser, and eventually detect fluorescence with photomultiplier tubes. So there are a number of features of thorium oxide. I won't dwell on many of these, but just to point out that it had lots of the right features to do this sort of measurement. Among them was the fact that this particular type of molecular state has a symmetry where the electrons spin and orbital magnetic moments almost exactly cancel each other, so that we're fantastically insensitive to magnetic fields while still being very sensitive to the electric dipole moment. One of the features that's maybe worth talking about a little bit more is that in these molecules there are structural features that are quite unlike anything that you've typically seen as an undergraduate when you talk about atoms. And here's an example that we take advantage of. Imagine you've got a molecule, as we have, in a triplet state, so the spin can be up, down, or sideways. But then the molecule can be oriented, the molecular axis can be oriented relative to this spin, either along the spin or against the spin, and those 2 configurations are mirror images of each other and must be nominally degenerate with each other. So just like we're used to from the undergraduate idea of an ammonia molecule where there are mirror image states, the actual energy eigenstates are even and odd superpositions of the mirror image states and very close together in energy. What we do is take these 2 states, which are states of opposite parity, and apply, and very close together in energy, apply an electric field to mix them via the Stark effect. We get an energy level structure that looks like this. If the molecule polarizes along the direction of the electric field, that minimizes its energy and gives us 2 states where the electron spin can be up or down relative to this polarization of the molecule. There's also a pair of states that goes up in energy with the electric field. That corresponds to a molecule that's polarized in the direction opposite what you would ordinarily expect, but they're perfectly good quantum eigenstates, and again, the electron spin can be up or down relative to the molecular axis here. So in ACME, we do the experiment just as I described before. We prepare a superposition of spin up and spin down in this pair of molecular states where the electron experiences an effective field pointing up in this picture. Then we can flip the electric field and look for the spin precession to change as I described. Or we can leave the electric field alone and instead prepare the molecule in this set of states, where everything is the same except the molecular polarization, and therefore the internal intramolecular field has flipped direction. That gives us a way to change the direction of precession of the electron if it has an electric dipole moment without ever having to change the external electric field, though we also do that. By doing this comparison, whoops, going the wrong way here. By doing this comparison, many possible systematic errors cancel in the comparison between the two states where the molecule is polarized in opposite directions. So here's a schematic of the experiment. It starts with this cryogenic molecular beam source that I mentioned before. There's a region where we use a handful of lasers to cool the rotational motion of the molecule, essentially try to collapse the Boltzmann distribution to get as many of the molecules in a single state as possible. Then it enters a region with parallel electric and magnetic fields, all surrounded by magnetic shielding. There are a set of lasers that populate the metastable triplet state and then spin polarize the electrons. Molecules then fly for about a millisecond in a region where there's only the parallel electric and magnetic fields. And then at the end, we detect what's happened to the spin, essentially by scattering polarized laser light. The scattering cross-section depends on the relative orientation of the electron spin and the laser polarization. That allows us to read out the final direction of the electron spin. To give you a sense of what the apparatus looks like, our electric field plates are actually glass coated with a transparent conductive coating. Here's the main vacuum chamber, end caps of magnetic shielding, the cryogenic beam source. Here's the apparatus buttoned up inside its 5 layers of magnetic shielding. Inside the shield is a series of magnetic field coils so we control the field. Here's a size scale in collider units for folks who are more used to that scale of experiment. And then the experiment uses on the order of half a dozen different lasers, fairly complicated optical system. Our control room is a couple of PCs shoved in the corner of the lab and driven by 1 or 2 graduate students at a time. So here's what data looks like typically. So this is our spin rotation signal that allows us to read out the direction of the electron spin at the end of the interaction region. We typically set the parameters of the experiment so we're here, and as the electron spin precesses, that corresponds to a signal that rides up and down this slope, and we look for the signal riding up and down the slope as we flip the electric field or the internal polarization of the molecules. So as promised, we spent a lot of time changing parameters in the experiment. We flip the internal polarization of the molecules about every half a second, the external electric field every second or so, and then we have additional changes including the magnetic field and the laser polarizations that essentially allow us to calibrate our sensitivity but also check for certain systematic errors. So I emphasize these switches because this strategy is really critical to how we check for systematic errors in the experiment. Let me try to explain that a little bit here. So in the end, we're able to measure the angle through which the electron is precessed as it flies through our experiment. We decompose that angle into components that are odd under different parameters that we reversed in the experiment. So there's an overall angle that doesn't change no matter what we do. There's an angle which is odd when we reverse the electric field, but not when we reverse the magnetic field or the internal molecular polarization. And this one is the phase precession angle that reverses sign when we switch the external electric field and when we flip the internal polarization of the molecule over. This is the one that contains the EDM phase. All these other ones are used as diagnostics for systematic errors. And each one of these phases we know contains various physical contributions. For example, this one that contains the electric dipole moment signal also contains contributions from other possible things that are imperfections in the experiment. So for example, there can be imperfections when we apply the electric field to polarize the molecules. Our field plates have imperfect insulation between them That can induce a leakage current that creates a magnetic field that reverses with the electric field that can couple to the tiny magnetic moment of our state and causes systematic errors. But critical to our approach is that the various symmetries of the system ensure that systematic errors are due only to experimental imperfections. After all the quantum electrodynamic effects, the atomic physics, has to satisfy parity and time reversal symmetries, and the EDM doesn't. Right. The way that we control these contributions that we know could lead to systematic errors is by taking into account the fact that these imperfections usually appear, things like a leakage current, magnetic field, or a non-reversing electric field that can contribute to a systematic error, usually appear in these other phases but greatly amplified. So for example, this leakage current appears in the phase which does not reverse with the molecular polarization but with the electric field, but it appears with an amplification factor of 1,000. So this allows us to very effectively tell if we have a leakage current magnetic field in the system, and so on. So these other phases diagnose these imperfections. And this is great if you're smart enough to anticipate what sort of things are going to cause you a problem. But of course, usually we're not smart enough to anticipate everything that can cause a problem. So we have various strategies to account for things that we don't anticipate. In particular, we change all possible parameters in the experiment that shouldn't affect the electric dipole moment. For example, once the electric field is big enough the molecules are completely polarized, we change the magnitude of that field by a factor of 2 or 3 and make sure that our EDM signal doesn't change, and so on. We also deliberately screw up the experiment. We deliberately amplify many potential imperfections and look for any changes in our signals that we see and make sure we understand them. And we have a list of literally over 3 dozen things of this type that we change, and we typically spend about a year studying possible systematic errors from this, and then finally only take data for a few weeks once we are certain that we've understood and controlled our systematic errors. So in the end, the data set is very boring. It's a Gaussian. It's actually an incredibly perfect Gaussian. On a log scale, you see no deviation all the way out to the wings of the Gaussian. We analyze our data blind, so there's an offset until we assign our systematic and statistical error bars. And then finally, after assigning the error bars, we unblinded the data and found a result consistent with 0. So we set an upper limit that the electric dipole moment of the electron is less than about 9 times 10 to the minus 29 electron charge times centimeters. So to try to give you some context for what that means, here's a plot with a log scale for possible values of the electron EDM, the upper limits from prior experiments. The standard model is over here. Notice the scale break. It's more than 10 orders of magnitude away from anything before. The blue splotches are different variants of supersymmetric theories. These are some more general models in other colors here. And our ACME result improved the sensitivity or improved the upper bound by about a factor of 10 from anything before. And it was limited by statistics. So just to put this again in context, this is a nice plot from Jonathan Feng at UC Irvine that tries to give a very broad overview of the status of the field as of a few years ago. In green are some reasonable guesses for what a natural scale for supersymmetric particle masses to appear are. Here at the top in Higgs mass, so mass on the y-axis, superpartner families on the x-axis. And the LHC bounds have moved up a little bit, but not too much since then. You can see that already, assuming order unity CP odd phases, EDMs were pushing into an interesting region. But this was before ACME. And since ACME, now we're able to probe in these simple supersymmetric models up well towards 6 or 7 TeV for things like the selectron mass. But as has been pointed out by a number of authors, through 2-loop diagrams, we're actually sensitive to things like charginos and stop quarks at masses even beyond the reach of the LHC. So this means that if the CP violation is not deeply suppressed in these supersymmetric theories that our EDM results are really pushing the SUSY scale into quite unnatural regions. Just to give you a few different ways of thinking about what this means, so you can also use our limit to say something about couplings of standard model particles. So here's a two-loop diagram that can give rise to an electron EDM. If the Higgs has a small CP odd coupling to the top quark in addition to its ordinary CP even coupling. And this shows the limits from the LHC on the combination of the CP even coupling on the x-axis, the CP odd coupling on the y-axis. The standard model predicts CP even coupling of 1, CP odd coupling of 0. The LHC gives this sort of banana-shaped piece in parameter space. And our ACME result says that the CP odd coupling of the Higgs to the top has to be extraordinarily small, something like less than 1% of the CP even Higgs top coupling. So this is really telling us something interesting about standard model particles that's hard to get in any other way. Again, just trying to understand what this means, here's a nice plot that was made recently by Matt Rees from Harvard that shows in an axis that shows more generic physics to the left and less generic physics to the right. LHC searches, of course, have limited various types of particles up to masses of about a TeV. Flavor violating, the absence of non-standard model flavor violating signals from kaon experiments have ruled out flavor violating new physics up to very high mass scales. And EDMs are now, through various mechanisms, able to set limits on somewhat more generic types of new particles at even higher mass scales than directly accessible through the LHC. So let me just close by saying that we're far from done. Since our limit was published in 2014, we've started working on a second generation. Again, the same three old guys, the three PIs, and a new team of graduate students. And the bottom line is that this is short-term statistical sensitivity from generation 1. In the current generation, our error bars look like this for the same amount of integration time. So we're now in our final, we've spent our year studying systematic errors. We're taking our final data as we speak. And we, unless something goes wrong, we should have around a 10-fold improved sensitivity by the time we're done within a few months. So again, this nice plot from Jonathan Feng, just to show you what that means. Our ongoing experiment that should be done within a few months will be probing mass scales in a fairly generic way up to nearly 30 TeV, and in an even more generic way up to several TeV. So we're very excited about this. We think that ultimately this ACME technique can even push another order of magnitude further, corresponding to another factor of 3 in mass reach. So stay tuned. We should be able to tell you sometime this year whether there's anything new that's associated with CP violation in this mass range from the first purple arrows. So with that, I'll end, and thank you for your attention.
When you project a mass range like that, are you always using the maximum phase one? Because that can swing this into, it's a two-dimensional space all the time here.
Yeah,
so I don't, these things make me nervous always.
Absolutely, and this, because we don't know what framework to work in, we're just trying to give a general sense of what this means. Absolutely, these all assume phases that are of order unity. But of course, if the phase is 0.1, then it's pretty easy to see how to scale these things. You change the mass reach by order square root of 0.1. Yeah. But I think, one thing I didn't emphasize is, of course, we know that there should be new sources of CP violation in order to explain the baryon asymmetry of the universe. So and in a fairly generic way, it's hard to avoid introducing new sources of CP violation when you introduce new degrees of freedom. So, of course, there are no guarantees, but it's far from obvious why there should be new physics at the TeV scale that has nothing to do with CP violation. But maybe it doesn't. So, yeah.
Maybe for a collider physicist, a few weeks sounds like a short run for a statistically limited measurement. Is that because of the manpower, or it's difficult to keep these things going for a long time?
It's actually more that in order to have the systematic errors sufficiently well studied for a few weeks of data, we need to spend about a year studying the systematics. So if we want to take a year of data, we would need to spend a decade studying systematics. The systematic understanding is limited by statistics during the study of the systematic errors. Nevertheless, it's also true that you can see that within a few years we've managed to improve our signal rate by a factor of a few hundred. And we've thought that it's a better strategy to spend a few years getting the signal rate up. Once we've squeezed everything we can out, then we'll probably dig in and take data for as long as we can.
Okay, so David, thank you very much. Thanks to all the speakers in this session. Let's go have coffee and come back at 11 for the second session.